This lecture begins theme 3, where we'll be visiting the first million years in the universe's life. It also begins our steady march through the various periods in cosmological history. So I want to take a few moments to get our bearings and see what the next 24 lectures and 6 themes will bring us, using the timeline from lecture 5. So here we are at theme 3. Notice we're starting neither at the beginning nor at the end, but somewhere in the middle, at this crucial transition period within the first million years. It gives us a window on the even younger universe, but it also sets the stage for the birth of the first stars and galaxies. So theme 4 then picks up that story and traces the evolution of stars and galaxies from their birth to the present time. Theme 5 looks at an important piece of our own lineage, the construction of the many types of atoms that make up you and me. And part of that story goes back to the minute-old universe. And that prepares us to visit, in theme 6, the extremely young, nanosecond-old universe, when matter and forces first took on their current form. Now, up to this point, the story is remarkable in its coherence and completeness, but it lacks a launching mechanism. It lacks a theory for the bang in the Big Bang. So theme 7 will explore that theory. It's called inflation, and it has some wonderful and extraordinary consequences. And finally, as with any cosmological story, scientific or traditional, our own conscious presence raises broader, more philosophical questions that I'll briefly explore in theme 8, and that'll naturally bring this course to its close. So let's now begin our visit to the first million years. It's a great place to start for a number of reasons. It's the earliest time we can witness the universe directly via the microwave background, so it's on a secure observational footing. But it's also on a secure theoretical footing, because the conditions at this time are relatively simple and well understood. The microwave background also contains an absolute goldmine of information, partly about the universe as a whole, partly about the stars and galaxies that are soon to be born, and partly about the even younger universe, including the inflationary period. And lastly, from our perspective, a nice quality of the first million years is that the conditions are relatively easy to understand and intuit, as well as being stunningly impressive. As we'll see, this time is characterized by brilliantly colored skies and intense heat and loud semi-musical sound, all of which will meet in due course. So let's begin relatively gently by recalling that as we look out into the universe, we also look back in time. So a galaxy 5 billion light years away, we see as it was 5 billion years ago, not as it is now. So pushing this idea to its limit, if we look 14 billion light years away, we see the universe as it was 14 billion years ago. Well, what was going on 14 billion years ago? The universe was being born. So that's what we see, the universe's birth. Perhaps even more bizarre, it doesn't matter which direction we look at. All directions end far away in the universe's birth. So the amazing fact is that out there, beyond the stars and beyond the galaxies, lies an all-sky panorama of the Big Bang. It's just sitting there, waiting for us to study it. Using our picture of the astronomer's view of the universe, we can now ask, what do we see, if anything, of this outermost shell? Is the Big Bang visible? The answer is a very definite yes, and it's not difficult to see why. The Big Bang was very hot, and hot things glow brightly. In fact, for reasons we'll get to in a moment, the relevant temperature was 3000 degrees Kelvin. And we know from lecture 4 that a gas of this temperature glows with a powerful, deep orange light. So we expect to see, in every direction, a brilliant orange glow covering the sky. Well, this flies in the face of common sense, because the night sky is dark black, not bright orange. So something's clearly missing in our thinking. And what's missing is redshift. At such a huge distance, the redshift is enormous, and the orange light waves that are stretched 1,000-fold, from a millionth of a meter to 1,000th of a meter. That's a millimeter. And that's in the microwave part of the electromagnetic spectrum. So, the Big Bang is directly available for us to study as a panoramic microwave glow. This, of course, is the famous cosmic microwave background, or CMB for short. I never cease to be impressed by this. There are, in fact, as many microwave photons coming from the sky as there are photons of light coming from a full moon. So if by some quirk of evolution we developed microwave-sensitive eyes, at night we could see our surroundings and we would cast shadows by the light of creation. What an absolutely stunning notion. So when you next look out at the night sky, try to feel the presence of the microwave background, the glow from the Big Bang. It really is there, but your eyes don't see it because of its huge redshift. Now, before we proceed, let's clarify exactly what the microwave background actually is. For example, is it the Big Bang itself? The answer is no, it isn't. It's the universe 400,000 years after the Big Bang. And to see why this is, we need to look more closely at this outer portion of our astronomer's view of the universe. So furthest away, longest ago, sits the Big Bang itself. It's like the first second, if you want. Inward and to the right are forward in time. The universe starts out very hot, so hot that atoms can't yet form and the gas is ionized. Nuclei and electrons separately zoom around freely. This kind of gas is foggy. You can't see through it. So the early universe is filled with a bright, glowing fog. But as the years pass, the universe expands and cools. And after about 400,000 years, its temperature dropped past a critical value of 3,000 degrees, below which electrons become attached to nuclei, and atoms could finally form. Now, this transition also makes the fog clear, and since then, the universe has been transparent. So, we look out through the transparent universe up to, but no further than, this wall of brightly glowing fog. As the bright orange light crosses the universe on its way to us, its waves are stretched 1,000-fold by cosmic expansion, and they arrive as microwaves. So the microwave background comes from a wall of 3,000-degree glowing fog, 400,000 years after the Big Bang. Now, the thickness of this boundary in this diagram is a little bit misleading. Here's a more accurate diagram of cosmic history, with the Big Bang on the left and now on the right, 14 billion years later. If we match this to an 80-year-old human lifespan, then the Hubble telescope looks back to 10-year-old pre-teens. The James Webb Space Telescope will look back to 2-year-old children. But look where the microwave background is. At 400,000 years, it is equivalent to just 12 hours after conception. This isn't just the infant universe, nor is it even the embryonic universe. It's the pre-embryonic universe. And just as for humans, the universe at this time is radically different from the universe we know today. Now let's recast this using distance instead of time. Here's a 26-mile marathon race from us to the Big Bang. In this case, the microwave background is just 4 feet from the finishing tape. How frustrating. We can see almost to the Big Bang itself, but not quite. It's forever hidden behind an utterly impenetrable wall of fog. Let's now spend a few minutes looking at first the prediction and then the discovery of the microwave background, because it provides a nice example of the often confused and serendipitous nature of scientific progress. The story begins in the mid-1940s, when the theoretician George Gamow began to calculate what actually happens during the early phase of the Big Bang. See, Gamow wanted to see if the Big Bang could make all the different kinds of atoms we find around us, the chemical elements. Now, because you need over 1 billion degrees to make atomic nuclei, Gamow guessed, A, that the Big Bang might have been a very hot kind of fireball, and B, that the thermal radiation from this fireball might still be visible today, but redshifted into the microwave range. Now, at that time, the instruments were nowhere near sensitive enough to detect this radiation, so no one looked for it. And in addition, a year or two later, more detailed calculations by other people showed that most of the chemical elements are in fact made in stars, not in the Big Bang. So perhaps surprisingly, this early 1940s work by Gamow, which actually predicted the existence of a microwave background, essentially disappeared and was forgotten for about 15 years. It wasn't until the early 1960s that calculations of a hot Big Bang were done again, independently, by two groups, Yakov Zeldovich and collaborators in Moscow, and Jim Peebles and Robert Dicke at Princeton. As before, these calculations predicted the fireball's thermal radiation should be visible as redshifted microwaves. Now, Robert Dicke was also a superb experimentalist, and so he immediately set about building a detector to see if he could see this microwave emission. And by May 1964, the Princeton group were close to making their first measurements. Now, meanwhile, completely unknown to Dicke, an hour away at Bell Telephone Labs in Holmdel, New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were also trying to make an extremely sensitive microwave receiver, but for quite different reasons. This was the early days of satellite telecommunications, and to support NASA's ECHO project, Bell Labs had built a large microwave horn antenna. And by 1964, Penzias and Wilson had managed to make an accurate measurement of the microwave emission from the sky. But something was quite puzzling. Their signal was too strong. 35% came from the atmosphere, 10% came from their amplifier, leaving 55% unaccounted for. It came from all directions and was constant over time, and they were completely unable to explain it. Then one day, Penzias heard about the Princeton group's prediction of the microwave background emission from the Big Bang. And Penzias immediately phoned Dicke at Princeton, who happened to be in the middle of his weekly lunch meeting with his group. At the end of the conversation, Dicke put down the phone and famously said, "Well, boys, we've been scooped." And indeed they had. It was Penzias and Wilson who later received a Nobel Prize for discovering the cosmic microwave background, arguably the most important scientific discovery of the century, with the possible exception of Hubble's discovery of cosmic expansion. Now, I'd like to add that in retrospect, the background radiation had already been detected on several occasions by various different groups. But each time, it had either been sort of dismissed as too uncertain, or its significance hadn't been appreciated. In fact, this whole episode in the history of science is full of missed opportunities and confusion, and it reminds us that science rarely proceeds in a clean, linear fashion, especially in the midst of an unanticipated breakthrough, like the discovery of the microwave background. Now, as you might imagine, in the half-century since its discovery, the microwave background has been the focus of enormous scientific scrutiny. both observational and theoretical. So let's now leave those early days and come forward to look briefly at some of the more recent observations. Here's a selection of CMB instruments from the last decade. 2 are high in the Andes, and since our own atmosphere emits at least some microwaves, it's important to get above as much of it as possible. And of course, the best place to go is above the entire atmosphere, into orbit. And the most impressive results have come from satellites, including NASA's Cosmic Background Explorer, or COBE, and the Wilkinson Microwave Anisotropy Probe, or WMAP. It's named after David Wilkinson, whose long career in CMB studies began back in 1965 as one of the boys in Bob Dickey's group, scooped by Penzias and Wilson. Now, to show you how far technology's come in 50 years, WMAP was placed well beyond the Moon's orbit in a stable gravitational pocket called L2. It took data continuously for 5 years and generated an all-sky map about 1 million times more sensitive than those first detectors back in the 1960s. So let's now look at the kind of data these satellites have provided. As with any source of radiation, one of the first things astronomers ask is, what is its spectrum? How does its brightness change with wavelength? The reason is that a spectrum can tell you a huge amount about the source, and in this case, the source is the young universe. So in 1990, the COBE satellite made an extremely accurate measurement of the CMB spectrum. Now remember from Lecture 4, we are expecting some kind of thermal spectrum that is generated by the ceaseless collisions of nuclei and electrons in a hot gas. The Sun, for example, has an approximately thermal spectrum, since its light comes from a hot atmosphere. So here are the COBE data points, spanning wavelengths from 0.5 millimeter to 5 millimeters. Now, through these data points is plotted a theoretical, pure thermal spectrum, which, as you can see, matches the data stunningly well. I was actually present when this plot was first shown publicly at the January 1990 meeting of the American Astronomical Society in Washington, and the audience of almost 1,000 astronomers spontaneously stood up and applauded for almost a minute. The applause was, I think, really for 2 things. They were, of course, acknowledging the incredibly hard work and skill of the COBE scientists, but they were also expressing their delight and perhaps relief that the universe conforms to simple physics and might therefore be ultimately understandable. So what do we learn from this thermal spectrum? Recall from Lecture 4, for a thermal spectrum, the peak wavelength and overall intensity depend on the temperature of the object. So, what's the temperature of the microwave background? It's a very precise 2.725 plus or minus 0.002 degrees Kelvin. Now remember, degrees Kelvin are degrees centigrade above absolute zero. So 2.7 Kelvin is extremely cold. And this may strike you as odd, since the gas emitting it is so hot. But don't forget redshift. When a thermal spectrum is redshifted, it stays a thermal spectrum, and the shift to longer wavelengths corresponds exactly to a shift to lower temperature. So the microwave background redshift stretch factor of 1,000 takes a 3,000 degree thermal spectrum and turns it into a 3 degree thermal spectrum. Now, there is in fact another way to look at this. As the universe expands, its contents cool. And in the 14 billion years since the microwave background was formed, the universe has cooled from 3,000 degrees to 3 degrees Kelvin. And so the microwave background simply reflects the current temperature of the universe. Now, what else do we learn from the CMB spectrum? Well, the fact that it has a thermal shape immediately tells us that the young universe was hot, not cold. And hence cosmologists talk not just of the Big Bang, but it's the hot Big Bang. And this in turn means we can study the very early universe using our knowledge of high temperature physics, as we'll see in lecture 27. But perhaps more importantly, the precision of the thermal shape tells us that the young universe was in a particularly simple state, which physicists call thermodynamic equilibrium. In this state, all the various components, the light, the electrons, the nuclei, all exchange energy back and forth freely, and each has the same well-defined temperature. And this enormously simplifies the situation. To a physicist, hot gas in thermodynamic equilibrium is one of the easiest things to understand. This is sometimes hard for people to accept. One somehow expects the early universe to be desperately complex and difficult to understand, perhaps because it's such a remote and alien realm. Whereas in truth, it's much simpler to understand than almost everything that we find around us here on Earth. Let's now turn to the spatial properties of the microwave background. Since it's a 360-degree panorama, what image does it show? What patterns are visible, if any? Now, the first thing to realize is that what one sees depends very much on the degree of contrast enhancement. Just as normal photos look quite different as one fiddles with the contrast, so the microwave background looks quite different as one changes its contrast. Now, secondly, remember that all sky maps appear as ovals, a bit like the full Earth maps. So, at the lowest level of contrast, the microwave background looks completely uniform. Remember in lecture 3, this is the most spectacular demonstration of isotropy. The universe is amazingly similar in every direction. It also tells us that the young universe is very smooth. So long before there were any stars or galaxies, the universe was simply an infinite ocean of extremely uniform, hot, glowing gas. This is also good news for cosmology, because smooth gases are much easier to study than clumpy gases. If you now subtract the average brightness and contrast stretch by about 1,000, you see this odd pattern. It's a bit like a yin-yang symbol, whose technical name is a dipole, meaning there are two poles. There is a slightly brighter area here and a slightly dimmer area here, with a smooth change in between the two. The effect is rather interesting and is caused by the motion of our galaxy, the Milky Way, through space. See, if our galaxy is moving through the universe, then the microwave background is slightly Doppler shifted. It's bluer and brighter in the direction of motion, and it's redder and dimmer in the opposite direction. And these in turn correspond to slightly hotter and colder temperature ahead and behind. And the difference in temperature, delta T over T, gives us the velocity relative to the speed of light, v over c. Now, using this, it turns out that our galaxy is falling at 600 kilometers per second towards the constellation of Hydra in the southern hemisphere. Notice I used this word falling. What's happening is that although galaxies basically move with the overall Hubble expansion, they're also being pulled by their neighbor galaxies, and this adds a falling motion on top of the expansion motion, and that's what makes the CMB dipole. What's causing our galaxy's motion is a huge assembly of thousands of galaxies sitting several hundred million light years away in the direction of Hydra, and we're effectively falling towards it at about 600 kilometers per second. Now, don't worry if you didn't quite follow that. We'll come back to this whole topic in lecture 22. Okay, Now, when we subtract the giant dipole pattern and contrast stretch again, there is a strong feature running across the sky caused by the microwave emission from our own Milky Way galaxy. Now, fortunately, as this spectrum shows, the Milky Way emission has a quite different spectral shape than the microwave background's thermal emission. And so as long as we have maps made at several different wavelengths, as all these WMAP images are, then you can remove this contaminating Milky Way emission to leave the pure microwave background image shown here in the middle. Now, this final microwave background image is extremely important in cosmology. But before looking at why, I just want to quickly review what we've done using a spherical depiction of the sky instead of an oval one. Here's a picture of the Earth, and from it we look out into space and see the optical celestial sphere with its stars and constellations. If we look at the same celestial sphere but using a microwave telescope, instead of seeing stars, we see an amazingly uniform microwave glow, which is shown here in green. If we then remove the subtle Doppler dipole and Milky Way emission and contrast stretch by about 100,000 times, this is what we see: slightly brighter and darker patches that cover the sky. We can see them all if we spin it around, like this. Now, this pattern is made from slight patches, from small to large, all randomly superposed on top of each other. The amplitude of the patchiness is about 1 in 100,000. And that's equivalent to the height of a bacterium on a bowling ball. So this patchiness is very, very slight indeed. Now, one can view these patches in two different ways, both of which are correct. First of all, they represent regions of slightly higher and lower density in the hot gas. The overdense regions contain slightly more mass, and gravity will ultimately pull them into galaxies and clusters of galaxies, while the slightly underdense regions contain slightly less mass, and these will ultimately become the spaces or voids between galaxies. So the patches are the seeds from which galaxies will grow, and we'll pursue this perspective in lectures 17 and 18. Now, the second way to view the brighter and darker patches are as the peaks and troughs of sound waves. You see, the higher and lower density, together with higher and lower temperature, makes higher and lower pressure in the hot gas. But pressure variations are, in fact, sound waves. So the microwave background gives us a freeze frame image of sound waves in the early universe. They're caught as they cross this wall of fog. And we'll pursue this perspective in lectures 15 and 16. Now, it may not be obvious to you as you look at this image, but this patchiness contains a huge amount of information. Now, what exactly we'll be talking about in the next couple of lectures. But to illustrate this richness of information, I'd like to end by briefly developing a metaphor that parallels the time of the microwave background with the equivalent time in a human's life, just 12 hours after conception. Now, in the case of a human, at that time, there are no structures, no arms or head or organs. There's just a single cell with its DNA. Now, likewise, in the universe at that time, there are no structures. There's no stars or galaxies or clusters. There's just uniform hot gas filled with sound waves. Now, for a human, that first DNA is immensely important. It determines, to a large extent, the future development of the child and adult. And it also contains a lot of ancestral, evolutionary information. So it is with the cosmic sound. It determines, in large part, how the universe of stars and galaxies will grow And it also contains information coming from much earlier times. So in a sense then, studying the microwave background and its patchiness is to astronomy what the Human Genome Project is to the life sciences. In fact, one might also almost call it Cosmic Genome Project. Well, with this introduction now in place, we're ready to visit the first million years. What was it like back then? What would we have seen and felt and heard? And why were there sound waves? And what can we learn about the universe by listening to them? Well, we'll find out in the next 3 lectures.